The crystal field theory was proposed by Hans Bethe and Van Vleck. This theory gives a much more satisfactory explanation for the bonding and the properties of complexes than the valence bond theory. The crystal field theory is based on certain assumptions. The interaction between the metal ion and the ligand is purely electrostatic. That is, the metal-ligand bonds are 100% ionic in nature. Negative ligands are treated as point charges, and neutral ligands are treated as dipoles. Thus, the bonding in the complex may be an ion-ion interaction or an ion-dipole interaction. The 5d orbitals in an isolated gaseous metal atom or ion are degenerate. That is, they all have the same energy. However, when the ligands approach the metal ion to form a complex, the electrons in the d orbitals of the metal will be repelled by the negative charge or lone pair electrons of the ligands due to the repulsion between the like charges. As a result, the energy of the d orbitals increases and the degeneracy of the d orbitals is lifted. It results in the splitting of the d orbitals. The pattern of splitting of the d orbitals depends on the number of ligands and their arrangement around the central metal atom or ion. Let's look at the application of the crystal field theory to octahedral complexes. In octahedral complexes, the metal ion is at the center of the octahedron, and the 6 ligands lie at the 6 corners of the octahedron along the 3 axes X, Y, and Z as shown here. The approach of the ligands towards the central metal ion is considered a 2-step process. In the first step, it is assumed that the ligands approach the metal ion spherically, that is, at the same distance from each d orbital. At this stage, the energy of all the d orbitals is raised by the same amount. That is, the 5 d orbitals still remain degenerate. The average value of the energy of the d orbitals at this stage is taken as 0, and this is called the barycenter. However, out of the 5 d orbitals, 2, that is, the dx square minus y square and dz square orbitals, which are collectively known as the Eg set of orbitals, are oriented along the axes towards the direction of the ligands. Thus, the Eg set of orbitals will experience more repulsion than the remaining 3 d orbitals. That is, the dxy, dxz, and dyz orbitals, which lie in between the axes. These 3 d orbitals are collectively known as the T2g set of orbitals. Consequently, the energy of the Eg set of orbitals increases, while that of the T2g set decreases relative to the average energy in the spherical crystal field. Thus, under the influence of the ligands, the degeneracy of the 5d orbitals of the metal ion is lost, and they are split into two groups of different energies. This effect is known as crystal field splitting. The extent of the splitting in energies is represented by the symbol delta O. The subscript O indicates octahedral geometry. Due to this splitting, the energy of the two Eg orbitals will increase by 3/5 of delta O, while that of the three T2G orbitals will decrease by 2/5 of delta O. The magnitude of crystal field splitting depends upon the field strength of the ligand and the charge on the metal ion. Ligands that cause only a small degree of crystal field splitting are termed weak field ligands, while ligands that cause a large splitting are called strong field ligands. In general, the common ligands can be arranged in ascending order of field strength as shown here. The order remains practically constant for different metals, and this series is called the spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Now, let's assign electrons in the d orbitals of the metal ion with d4 configuration in the octahedral coordination entities. Obviously, the first, second, and third electrons occupy the low-energy T2G orbitals in accordance with Hund's rule. However, for the fourth electron, there are two possibilities. The first possibility is that it may enter a T2G orbital and pair up with an existing electron there. The other possibility is that it may enter the higher Eg orbitals. The exact path followed by the electron depends on the relative magnitude of the crystal field splitting, delta O, and the energy required for the electron pairing in a single orbital, that is, pairing energy B. If the crystal field splitting energy is less than the pairing energy, then the fourth electron enters one of the higher energy Eg orbitals, giving the configuration T2G3 Eg1. Ligands for which the crystal field splitting energy is less than the pairing energy are known as weak field ligands. The complexes formed with these ligands would be high-spin complexes. If the crystal field splitting energy is higher than the pairing energy, then the fourth electron enters a T2G orbital and pairs up with one of the electrons, giving the configuration T2G4 Eg0. Ligands for which the crystal field splitting energy is higher than the pairing energy are known as strong field ligands. The complexes formed with these ligands would be the low-spin complexes. Now, let's look at the crystal field splitting in tetrahedral complexes. The approach of the ligands in a tetrahedral field is as shown in the figure. You can observe from the figure that the ligands interact more with the T2G orbitals than the EG orbitals lying between the axes. This is because the T2G orbitals are oriented along the direction of the approach of the ligands. Thus, in tetrahedral splitting, the T2G orbitals are of higher energy, and the two EG orbitals are of lower energy. You can say that the d orbital splitting in tetrahedral geometry is exactly the reverse of octahedral splitting. The crystal field splitting in tetrahedral complexes, which is denoted by delta T, is smaller than that of octahedral complexes. The difference in energy can be represented by delta T is equal to 4 by 9 times of octahedral splitting. This splitting energy is not large enough to force the electrons to get paired up. Thus, low spin configurations are rarely observed. Transition metal atoms or ions with one or more unpaired electrons and their complexes exhibit color both in their solid and solution states. Let us see how a substance gets its color. When white light passes through a substance, it absorbs some of the wavelengths. The light transmitted by the substances is deprived of the wavelengths that have been absorbed. If absorption occurs in the visible region of the spectrum, then the transmitted light has a color complementary to the color of the light absorbed. Complementary color is the color generated from the wavelength left after the absorption. For example, for hexaaccure titanium 3+, the maximum absorption occurs at 498 nanometer, which corresponds to the blue-green portion of light. The transmitted light is devoid of the blue-green portion, and hence the complex appears purple. The relationship between the absorbed and transmitted wavelengths can be readily understood from the table here. The origin of the color of coordination compounds can be readily explained in terms of the crystal field theory. As you have studied in the previous module, when a ligand approaches the metal ion containing unpaired electrons, the 5 degenerate d orbitals separate into two distinct energy levels, namely T2G and EG. When light of sufficient energy is incident on the metal ion, the electron in the low-energy T2G orbital absorbs energy and gets promoted to the higher EG set of orbitals. White light minus the absorbed color becomes the color of the complex. Thus, the color of coordination compounds arises from the electron transition between the split d orbital energy levels. Let us take the example of hexaaccure titanium 3 to understand this. Hexaaccure titanium 3 is an octahedral complex, in which titanium is in +3 oxidation state and has a single electron in the d orbital. The single electron is present in the lower T2G level in the ground state of the complex, When light passes through a solution of this complex, the electron in the lower T2G level is promoted to a higher EG level by absorbing light with energy equal to the energy difference between the T2G and EG levels. In this case, it absorbs energy corresponding to the blue-green region. As white light minus blue-green light gives purple color, the complex appears purple. The color of gemstones like ruby and emerald is also due to the D to D transition of electrons within the d orbitals of the transition metal ion. Ruby is a pink to blood red colored gemstone. It is aluminium oxide in which a small fraction of Al3+ ions are replaced by chromium 3+ ions. The red color of a ruby is mainly due to the presence of chromium 3 ions. We may view these chromium 3 ions as octahedral chromium 3 complexes incorporated into the alumina lattice. This crystallographic arrangement affects each chromium 3+ ion, resulting in the D to D transition of electrons after the absorption of the yellow-green portion of light. As white light minus yellow-green gives red color, a ruby looks red. Emerald is a green variety of the mineral beryl. The green color of emerald is due to the presence of chromium 3+ ions. The chromium 3+ ions occupy the octahedral sites in beryl. Due to this arrangement, it absorbs the yellow-red portion of light and, in turn, transmits the complementary color green. Hence, an emerald appears green. It is important to note that in the absence of a ligand, crystal field splitting does not occur. As a result, the substance remains colorless. For example, when hexa-aqua titanium 3+ is dehydrated by heating it, it becomes colorless. Similarly, hydrated copper sulfate is blue, while anhydrous copper sulfate is colorless. The influence of the ligand on the color of a complex may be demonstrated by considering the hexa-aqua nickel-2 complex. When nickel-2 chloride is dissolved in water, it gives the green hexa-aqua nickel-2 complex. To this complex, if the didentate ligand ethane 1,2-diamine is added progressively in different molar ratios, different complexes with varying colors are formed. When the addition of ethane 1,2-diamine to the complex is in the molar ratio of 1:1, a pale blue colored complex of tetra-aqua ethane 1,2-diamine nickel-2 is formed. When the addition is in the ratio of 2:1, a blue or purple colored di-aqua bis ethane 1,2-diamine nickel-2 is formed. Addition in the ratio of 3:1 results in a violet colored tris ethane 1,2-diamine nickel-2 complex. Now let us see the drawbacks of the crystal field theory. Although it successfully explains the formation, structure, color, and magnetic properties of coordination compounds satisfactorily to a large extent, it suffers from some drawbacks. If the assumption that anionic ligands are point charges is correct, then anionic ligands should act as strong ligands, and hence should exert the greater splitting effect. However, anionic ligands are actually found at the low end of the spectrochemical series. The other drawback is that it does not take into account the covalent character of bonding between the ligand and the central atom. Two or more compounds with the same chemical formula but different structural arrangements are called isomers. The phenomenon is known as isomerism. Isomers differ in one or more physical or chemical properties because of the difference in the arrangement of the atoms. Isomerism in coordination compounds may be broadly divided into two types: structural isomerism and stereoisomerism. Structural isomerism arises due to the presence of different kinds of bonds between the metal and the ligands. This can be further subdivided into several types, like ionization isomerism, solvate isomerism, ligand isomerism, linkage isomerism, polymerization isomerism, coordination isomerism, and coordination position isomerism. Of these, we will discuss only ionization isomerism, solvate isomerism, linkage isomerism, and coordination isomerism in this module. Let us first discuss ionization isomerism. Compounds that have the same stoichiometric composition but yield different ions in a solution are called ionization isomers. This type of isomerism is due to the exchange of groups between the complex ion and the ions outside it. The composition can be determined by a precipitation reaction. Pentaamine sulfato-cobalt 3 bromide and pentaamine bromido-cobalt 3 sulfate are two ionization isomers. The first isomer gives a white precipitate of barium sulfate with barium chloride solution, thus confirming the presence of free sulfate ions. By contrast, the other isomer does not give a positive sulfate test. It does give a pale yellow precipitate of silver bromide with silver nitrate, confirming the presence of free bromide ions. Other examples of ionization isomers are tetraamine dichloridoplatinum 4-bromide and tetraamine dibromidoplatinum 4-chloride. Let us now look at solvate isomerism, which is similar to ionization isomerism. This form of isomerism is known as hydrate isomerism if water is involved as a solvent. compounds that have the same composition but differ by whether or not solvent molecules are present as ligands in the coordination sphere or are merely present as free solvent molecules outside the coordination sphere are known as solvate isomers. 3 isomers of chromium chloride hexahydrate CrCl3 6H2O are known. From conductivity measurements and quantitative precipitation of the ionized chlorine, they have been identified as the violet-colored hexa-aquochromium 3 chloride, the green-colored penta-aquochloride or chromium 3 chloride hydrate, and the dark green-colored tetra-aquo-dichloride or chromium 3 chloride dihydrate. These isomers have different chemical properties. On reacting with silver nitrate to test for Cl ions, we would find 3, 2, and 1 chloride ions in the solution respectively. The other type of structural isomerism is linkage isomerism. Linkage isomerism arises when a ligand can bind to a metal ion through any one of 2 or more different donor atoms. Thus, this type of isomerism is seen in the coordination compounds that have ambidentate ligands. For example, in the ambidentate nitrite ion, either nitrogen or oxygen atoms could act as the electron pair donors. Thus, there is a possibility of isomerism. 2 different complexes, each containing nitrite ions, have been prepared. For example, red pentaamine nitrito-cobalt 3 chloride, in which the nitrite ligand is bound through oxygen, and yellow pentaamine nitro-cobalt 3 chloride, in which the nitrite ligand is bound through nitrogen to the metal ion. Similarly, the thiocyanate ligand, SCN, may bind to the metal through sulfur to give complexes of the type MsCN or through nitrogen to give MnCS type of complexes. Coordination isomerism is another type of structural isomerism. This type of isomerism arises when both the positive and negative ions are complex ions. It may be caused by an interchange of ligands between the anion and the cation. For example, in the complex hexaamine cobalt 3 and hexacyanochromate 3, the ammonia ligands are bound to the cobalt 3 plus ion, while the cyanide ligands are bound to the chromium 3 plus ions. In its coordination isomer, hexaamine chromium 3 hexacyanocobaltate 3, the ammonia ligands are bound to the chromium 3, while the cyanide ligands are bound to the cobalt 3 plus ions. Let's now look at stereoisomerism. Compounds with the same chemical formula and chemical bonds, but different arrangement of atoms or groups in space, are called stereoisomers. Stereoisomerism can be subdivided into geometrical isomerism and optical isomerism. Geometrical isomerism is also known as cis-trans isomerism. It is seen in the heteroleptic complexes with coordination numbers 4 and 6. The isomer in which the two identical groups are adjacent to each other is known as a cis isomer, while the isomer in which the two identical groups are diagonally opposite to each other is known as a trans isomer. It is important to note that only square planar complexes show the phenomenon of geometrical isomerism, and not tetrahedral complexes. This is because the relative positions of the unidentate ligands attached to the central metal atom in the tetrahedral geometry are the same with respect to each other. In square planar complexes, compounds with the general formula Ma4 and Ma3b do not show geometrical isomerism. Here, M is a metal ion, while A and B are monodentate ligands. The square planar complexes shown here usually show cis-trans isomerism. The first complex is of the type Ma2b2. The best example of this type is diamine dichloridoplatinum 2. Both cis and trans isomers of this complex are shown here. The second complex is of the type Ma2bc. Diamine bromidochloridoplatinum 2 is an example of this type of complex. Another type of square planar complex is the MaBCD type. Platinum 2 forms a number of complexes of this type. Such complexes exist in three isomeric forms. For example, amine bromidochloridomyridine platinum 2. The three isomers of this complex can be seen here. Now, let's look at the geometrical isomerism in octahedral complexes. Ma6 or Ma5b types of octahedral complexes do not show geometrical isomerism. Complexes of the type Ma4b2 and Ma3b3 and complexes that have unidentate and symmetrical bidentate chelating ligands of the type MAA2b2 exhibit geometrical isomerism. Dichloridotetraamine cobalt 3 is an important example of a complex of the Ma4b2 type. The cis and trans isomers of this complex are shown here. An important Ma3b3 type of complex is trichlorido-tripyridine rhodium 3. In one of the isomers shown, you can see the three donor atoms of the same type of ligands occupying adjacent positions at the corners of an octahedral face. Such an isomer is known as a facial isomer. In the other isomer, called a meridional isomer, the position of the ligands are around the meridian of the octahedron. Now, let's look at MAA2b2 type of complexes containing monodentate and symmetrical bidentate chelating ligands. Here, AA is a symmetrical bidentate chelating ligand in which A and A indicate two similar coordinating atoms, while B is a monodentate ligand. The cis and trans isomers of dichlorido-bis-ethylene diamine cobalt-3 are shown here. Let's examine optical isomerism, which is the other type of stereoisomerism. When the solutions of certain coordination compounds are placed in the path of plane polarized light, they rotate its plane through a certain angle that may be either to the left or to the right. This property of a complex of rotating the plane of a polarized light is called its optical activity. A complex that possesses this property is said to be optically active. Complexes that rotate the plane of polarized light towards right are said to be dextrorotatory or D-form, while complexes that rotated towards the left are called levorotatory or L-form. The D and L forms are mirror images and cannot be superimposed on each other. Such molecules or ions that cannot be superimposed are called chiral. Since these forms are related to each other as mirror images, they are commonly called enantiomers. Although optical isomerism is possible in a variety of octahedral complexes with unidentate ligands of the types Ma2b2c2, Ma2b2cd, Ma2bcde, and MABCDEF. We will restrict our discussion to complexes containing only bidentate ligands of the type MAA3 and complexes containing monodentate and symmetrical bidentate chelating ligands of the type MAA2B2. Tris-ethylene diamine cobalt-3 is the best example of an optically active coordination compound of the type MAA3, which has only bidentate ligands. The dextro and levo isomers of this complex are shown here. Dichlorido-bis-ethylene diamine platinum-4 is an example of an optically active coordination compound of the type MAA2B2 containing both monodentate and symmetrical bidentate ligands. Note that only the cis isomer of this complex shows optical activity. Its trans isomer shown here is optically inactive because its mirror image can be superimposed on itself.